So today we are going to solve a special problem on hydrodynamic channel bearing. So in this problem, based on the load and minimum film thickness, we are going to select the lubrication oil and we are going to calculate the remaining parameters. Okay. So this problem is not like the previous design problem. So it is somewhat different and it is actually a special case problem. Okay. But the problem is very simple. All the data are in the data book. You have to refer a chart and you have to take the values and you have to substitute it. You have to find the solution. Okay. Fine. So I will directly start the problem and I will explain the concept in between the steps. So the problem is a load of 100 full hydrodynamic channel bearing is 9000 Newton. So the load is given, it is 9000 Newton. So I have converted it into kgf. Okay, so we have to divide 9.81 or otherwise you can divide 10 to convert Newton into kgf. So it is 900 kgf. So the speed of the channel is 320 rpm. Then let L by D is equal to 1 and C by D is equal to 0.011. 0011. Okay. So L by D is given as 1, but the diameter value is given in 10 centimeter. So I can substitute the value of diameter and I can calculate the length. So length is equal to 10 centimeter. Further, C by D ratio is given, that is C by D is equal to 0.011. So C is equal to, so if C by D is equal to 0.1011, then further Z is equal to 0.11 into D. Okay, so like that we can calculate the value of D. Then the operating temperature TO is given as 65 degrees Celsius. So TO is 65 degrees Celsius and the minimum oil film thickness is equal to 0.002 mm. So that is H naught. Okay. So the important key parameter to identify this type of problem is the minimum film thickness. Okay. So if the minimum film thickness is given, then you should not use the previous procedure to design the bearing. Okay. So select an oil that will closely accord with the stated conditions. So first step we have to select an lubrication oil. Then second step, for the selected oil, determine the friction loss, then hydrodynamic oil through the bearing. So that is the hydrodynamic oil flow through the bearing, then the amount of leakage, then the temperature rise of oil passes through the bearing, and finally the maximum oil pressure. Okay. So first we'll calculate, first we'll select the lubrication oil, then I'll tell you how to select the remaining parameters. Okay. So this is the chart that we should follow. So this chart is there in the data book page number 7.36. Okay, so actually you have charts from 7.36 to 7.40, but you have to look into the title of the chart. So here in the problem, it is actually a full hydrodynamic bearing. So that is why I have considered this. You can see the chart. You can see the problem. Yeah, here it is. It's a full hydrodynamic bearing. So that is why I am going to refer the chart. So similarly, we have 180 degree bearing and 90 degree bearing. So before selecting the data from the table, be clear about the title. So it is full channel bearing. Okay, so two data are needed to select the parameters. First one is the L by D ratio. Then second one is the 2H0 by C. So if you know the L by D ratio and 2H0 by C, then we can select the remaining values, that is S, phi and all those things. Okay. So first I will calculate the 2H0 by C because in the problem H0 value is given and C value is also given. So 2H0 by C is equal to 2 into H value is given as 0.0022, then C value is given as 0.011. Okay. So 2H0 by C is equal to 0.4, then L by D ratio is given as 1. Okay. So we have L by D ratio of infinity, we have 1, then further in the bottom you may have 0.5 and 0.25. So for me the L by D ratio is 1. Okay. So we have to focus on this region. And next look into the 2H naught by C, and in the problem the 2H naught by C value is 0.4. So yeah, here it is 0.4. Okay, so we have to refer this row for the remaining calculations. Okay, so you can write all the values, that is S is equal to then mu d by C. So similarly in your note you can write all the values first. Okay, then we'll move into the next procedure. Yeah, so first to select the lubrication oil we have to calculate the Sommerfeld number. So Sommerfeld number is a dimensionless number. So it's actually a relationship between the pressure and the absolute viscosity. Okay, so S is equal to Z dash N dash divided by P d by C the whole square. Okay, so this equation is there in data book page number 7.34. You can refer that. So here Z dash is not actually in centipoise, it is actually in kg of second per centimeter square. So further the kg of second per centimeter square is equal to Z divided by 9.81 into 10 power 7. So this conversion is also there in the right side of page number 7.34. Okay, so here the S is the Sommerfeld number, and in the previous step I have taken the S value from the chart. So that S value from the chart is 0.121. Okay, so you can refer the table 1. So Z dash I have to calculate, then N dash is speed in RPS, it is not RPM. So N dash is equal to speed in RPS, that is 320 is speed in RPM divided by 60, so that you will get 5.33 RPS. Okay, so 5.33, then P is the allowable bearing pressure, so that we have to calculate. So we know that the equation for P is equal to W divided by LD, that is allowable bearing pressure. So we might have studied these equations earlier. So the W is 900 kgf. So remember that here you have to substitute the values in kgf and centimeter. So it is 900 kgf and the length is 10 centimeter and diameter is 10 centimeter. So if you solve this, you will get the allowable bearing pressure value as 9 kgf per centimeter square. You can substitute it. Then D is the diameter, C is the diametral clearance. Okay, so remember that S is the Sommerfeld number that we have taken from. So S value we have taken from table 1 from PSGDB 7.36. Okay, then Z dash is absolute viscosity in kg of second per centimeter square. So that is equal to Z divided by 9.81 into 10 power 7. Anyway, we have to find out the Z dash value. Then N dash is equal to speed in RPS, that is 320 divided by 60. Then D is diameter, C is clearance ratio, and P is the allowable bearing pressure that we have to calculate. So the equation is P is equal to W divided by LD. So you can substitute all the values and you can calculate the value of Z dash. So the calculated Z dash value is 2.5 into 10 power minus 7 kgf per centimeter square. So but we need the Z dash value in Z value in centipoise to select the standard lubrication oil. So we can convert the Z dash value into centipoise by using this relation. So Z dash is equal to Z divided by 9.81 into 10 power 7. So this relation is there in data book page number 7.34. So if you substitute the value of Z dash and if you Z, then you can calculate. So it is not actually 1.2 into 10 power 6. It is 2.5 into 10 power minus 7. So that is what we have calculated earlier. Okay, so there is a small mistake there. Okay, so then you can calculate the value of Z, that is equal to 24 centipoise. Okay, so now I have calculated the value of Z. Then I can select the standard lubrication from PH data book 7.41. So we have Z is equal to 24 centipoise and the operating temperature is given in the problem, that is 65 degrees Celsius. So we know how to select the lubrication oil when we know the Z value and operating temperature. Okay, so the x-axis in the plot is temperature, so mark it is 65 degrees Celsius, and the value is 24 degrees Celsius. Okay, I mean 24 centipoise. So it will go like this. Okay, so around here. So this is our point. So the next standard oil is SAE 30. Okay, so the selected lubrication for this lubricating oil for this purpose is SAE 30 oil. Okay, so this is how we have to select the lubrication oil. So the first step is very important, that is calculation of Sommerfeld number. So after calculating the Sommerfeld number, you can use the Z value to select the lubrication oil. Then the second step is friction loss. So friction loss means it is actually the heat generated, because the heat is generated because of friction. So Hg is actually the friction loss, and we know that Hg is equal to mu W into V, and for calculating Hg value we have to follow Newton and meter. Okay, fine. So here W is the load acting in Newton. We know that V is the velocity in meter per second. V is equal to pi dn by 60. So if you substitute the diameter value in meter, you will get the answer in meter per second. So I have substituted the diameter value in meter. So the velocity is 1.67 meter per second. But here I don't know the value of the mu. So actually in the design procedure we will calculate the mu value separately. But here we have the mu d by c value from the data book. So in the data, in the table 1, that is the previous table what we have referred, the mu d by c value is 3.22. You can see that. Yeah. So here, so the mu d by c value, sorry. So here the mu d by c value for 0.4, it is 3.22. Okay, fine. So I am going to use the value here. So mu by d by c is equal to 3.22. So here mu is equal to 3.22 into c divided by d. So c value is given in the problem, it is 0.011, and d is given, it is 10 centimeter. So I can calculate the mu value, that is 3.5 into 10 power minus 3. Okay. So once after calculating the value of mu, I can substitute everything in the Hg equation and I can calculate the Hg value. So remember that while calculating Hg, you have to substitute the W value in Newton, V value in meter per second. So the friction loss is 52.6 watt. Then the next step is total oil flow. Okay, so from the table we can take 4Q by DC n dash L is equal to 4.33. So further Q is equal to 4.33. You can bring the remaining terms to the right side. So here Q is the total oil flow. So it is D C n dash L divided by 4. So here D is the diameter, C is the clearance, n dash is speed in RPS. Remember that n dash is equal to speed in RPS. It is not in RPM. So n means it is RPM, n dash means it is RPS. Okay. So you can then L is the length of the bearing. So all the data are given. You can refer the given data. So you can substitute it. D is 10 centimeter. C dash is 0.011. N dash is 5.33. We have calculated earlier. L is 10. So if you substitute all the values, you will get Q value in centimeter cube per second, because I have substituted the value in centimeter and second. Then the next one is side leakage. So in the table you can find another value, that is Q naught by Q is equal to 0.68. Okay, so here Q naught is the leakage and Q is the total oil flow. So Q we have calculated in the previous step. You can substitute the value of Q and you can calculate the value of Q naught. So the calculated Q naught value is 4.28 centimeter cube per second. The fifth one is temperature rise. So the another term from the table is rho C dash del T naught by P, that is equal to 14.2. So here del theta is, del T is the temperature difference. So you can keep del T and you can bring the remaining terms to the right side. That is 4.22 P divided by rho C dash. So P is the pressure value in kgf per centimeter square. We have calculated in the previous step. Then the rho C dash value is given in the data book page number 7.36. So at the bottom of the chart you can see that. So rho C dash value is equal to 14.2 kgf per centimeter square degree Celsius. You can substitute it. So if you solve this, then you will get del T value as 9 degrees Celsius. That is the temperature rise. Then the last step is calculation of maximum pressure. So from the table, P by P max is equal to 0.415. So here P is the pressure value and P max is the maximum pressure. So further P max is equal to P divided by 0.415. P we have calculated, it is 9. So the P max value, that is maximum pressure, is 21.68 kgf per centimeter square. Okay, so this is how you have to approach the problem when the minimum oil film thickness is given. So the calculation of Sommerfeld number is very important. So once after calculating the Sommerfeld number and the absolute viscosity, then the remaining procedure is simple. So you can take the values from data book. You can see that. So all the data values are given here. So mu d by c is given, 4q divided by dc n dash l is given, q naught by q is given, then rho c dash del t by p is given, and finally p by p max is also given. So you can take the values, you can substitute the known values and you can calculate the unknown values. Okay, so this is how you have to solve the problems on hydrodynamic channel bearings. So the tutorial problem. The load on a 100 mm full dynamic channel bearing is 8000 Newton. So the diameter is 100 mm, that is 10 centimeter. The load is 8000 Newton. I have converted it into kgf, that is 800 kgf. The speed of the channel is 320 rpm. This is n, not n dash. To calculate the value of n dash, you have to divide n divided by 60. Okay. Then L by D is 1, C by D is 0.001. The operating temperature is 60 degrees Celsius. So in this kind of problems, they will not ask you to design the bearing. So you can identify the problem by this term. So if the minimum oil film thickness is given, then you should not design the bearing. You have to calculate the Sommerfeld number. Okay, so actually in channel bearing, we have two procedures. One is the design of channel bearings. That is what we have discussed in the previous two lectures. Then this problem is based on Sommerfeld number, and to identify the problem, you can refer this term, that is minimum oil film thickness will be given. Select an oil. So you have to select an oil. Then for the selected oil, calculate friction loss. So that is Hg. Then hydrodynamic oil flow through the bearing, that is Q. Then the amount of leakage, that is Q naught. Then the temperature rise, that is del T. And the maximum oil pressure, that is P maximum. Okay. So the problem is same like the previous problem. You can refer the previous classwork problem and you can solve the tutorial problem.